welcome. We're going to start in a couple of minutes. But while people are getting their settings organized, perhaps I can just give you some logistical information. So if we can just go to the next slide, please. So we will have for today's webinar interpretation. So something that you need to check is at the bottom of your screen, you have the interpretation button, just as the little square, black square that you have on the screen. If you do not see this button, it means that you might have an old Zoom link. So we will appreciate if you can just upload again go to Zoom, the link that is on the screen, and that you can upload it again, so you can actually access both the English and Spanish function. Next slide, please. So just some information, a disclaimer: interpretation of remote meetings on Zoom serves to facilitate communication and do not constitute an authentic record. Only the original speech is authentic, so the English version, and interventions that are read out too fast or where the sound quality is insufficient may have to go uninterpreted. So just a reminder for our speakers and myself that we have to speak loud, slowly and clear, so we can have like a good translation. Okay, we go to the next slide. So you will see that in these Zoom facilities, we have several buttons. So some that we would like you to pay attention to is the function Q&A next to the chat box. So if you have any question, whether it is in English or Spanish to the panelists, please type it via this link, because it's the only link that is accessible to our panelists. On the other hand, there is a function chat that you might be more familiar with, and that we will be using, my colleague Leslie and myself, to upload links that are related to the documents or to the presentations that you will be listening today. If you have any problem, technical problem that you cannot hear, you can also contact Leslie and myself via the chat, and we will be able to help you. So just with this webinar, as I mentioned, is going to be recorded, and it's going to be made available afterwards in both languages, so English and Spanish, and it's going to be available in the link that is in the slide. This said, do not worry, we will be sending you the link via the chat, but all registered participants will receive all the information afterwards, and you will be able to access the recording. Okay. So, next slide, please. So, I will be giving you a very quick introduction from on behalf of the OECD. So just to give you a little bit of context of the test guidelines that we will be discussing today, we have at OECD an agreement that is called the Mutual Acceptance of Data System. And this is mainly to say that data generated using OECD Test Guidelines, like the one that will be presented today, and that is done under good laboratory practices, is accepted across member countries and MAD adherence. And this means that, that you only have to test it once, and that is going to be accepted everywhere. So this is really like to reduce costs, to reduce use of animals, etc. There are some links that we will be, as I said, share with you on the chat, where you can have more information about the mutual acceptance of data. And there have been a number of webinars to explain this in more detail available at the OECD website. Next slide. So just to share with you just a quick slide, just to explain you that coming today, and we are very proud to come today to share with you this test guideline, because this is not an easy endeavor. So we have a whole process that will ensure that the test guidelines that are being proposed are addressing some regulatory requirements, that the test method is properly validated, that is reproducible, that is repeatable, and that we can have certainty in the result that is given. And this is why this is part of the OECD mutual acceptance of data. Today, if you go to the next slide, we're going to discuss the most recent test guideline, which is on the determination of surface hydrophobicity of manufactured nanomaterials. We will have the whole presentation shortly, but this slide is just to say that this is part of bigger efforts that we have been doing at the OECD to develop test guidelines that are applicable to manufacture nanomaterials. Some of them have already been published, and some of them are on the way, and we hope that they will be made available in the coming year. Next slide. So today's speakers have something in common on top of this nice test guideline, is that they all come from the European Commission Joint Research Center. The speakers that we will have today, they all have been the authors and the minds behind the development of this test guideline, so you will have firsthand information. So if you allow me just to introduce them. So we have Juan Riego Sintes. Dr. Juan Riego Sintes leads the Nano Governance and Regulatory Methods team since 1996 at the GRC. He coordinates chemical test methods and guidelines, chairs the European National Coordinators, and has also been representing the Commission in the OECD Test Guidelines Program as an EU National Coordinator. He's also a long-standing member of the OECD Working Party on Manufactured Nanomaterials, where he has been leading the development of several documents, and he has also been chairing the steering group on the testing and assessment. He's the author of more than 80 publications. He has been an active participant in many research projects, such as Marina, NanoReg, Go4Nano, Sonchan, just to name a few. And before he entered his regulatory area, he also worked on organic synthesis with hydrates, heterogeneous catalysis, with supported regions, supramolecular chemistry, molecular recognition, and environmental chemistry. So thank you, Juan, for being here today with us. Then we will have Dr. Chloe Desmet, who's a scientific officer at the GRC, Technologies for Health Unit. Chloe Desmet obtained her PhD in biochemistry in 2013 from the University of Lyon on the development of sensors for the multiplex detections of biological markers and chemicals, and dedicated to diagnostic and environmental monitoring. She joined the GRC in the nanobioscience unit for 3 years, where she could deepen her expertise in the field of nanomaterials. And in 2017, she moved to the CEA in Grenoble to bring her experience to a project aiming at the development of biosensors for in vivo diagnostic. Finally, we're lucky that she returned to the GRC to place her expertise at the service of the European Commission on EU policy support. And her current activities are mainly focused on studying biomolecular interactions and nanomaterials for projects on preparedness and innovation to tackle health challenges, as well as technologies and methods for monitoring micro and nanoplastic pollution. Another of our speakers is Francesco Roncari, who's a scientific project officer at the European Commission Joint Research Center, MISPRA, since November 2019. Francesco holds a master's degree in molecular and industrial biotechnology with a specialization in nanobiotechnology from University of Insubria Varese. His main activities are related to the physicochemical characterization of nanomaterials through different techniques, in particular dark field microscopy, dynamic light scattering, and single particle extinction and scattering. He's also expert in surface characterization and in microfluidic devices designed for 3D bioprinting applications and for cellular perfusion. And last but not least, we will have with us Dr. Andrea Valsesia, who has a PhD in physics on nanofabrication of surfaces for biological application. He has 20 years of experience in the field of nanomicrofabrication, thin film deposition, surface analysis and integration of devices, development of high-tech laboratory equipment, characterization of engineered nanomaterials. His research has been always oriented toward development of methods and experimental tools to support EU regulation, in particular in the nanotechnology domain. He was the founder of the spin-off company generated from the technology transfer project, Plasmor. He is official at the GRC since December 2013. In the last years, he managed 3 proof of principle projects and an exploration project, Sentinel. And from 2019 to 2020, he was visiting researcher at the National Institute of Standards and Technology in the US. So as you can see, we have a very rich expertise around the table today. And with that, and without entertaining a little bit more, I would just want to give the floor to Dr. Juan Riego Sintes, so we can start going a little bit more in depth in the work that they have been doing over the last several years. Thank you so much, Juan. The floor is yours.
Thank you very much, Mar, and thank you for your nice introduction to all of us. I will be the one that will present a little bit the background before the that led to the development of this new test guideline number 126 on the determination of the hydrophobicity index of nanomaterials through an affinity measurement. I have to say that my role has been mostly the consultancy and advising my colleagues. They are the real ones that have the technical expertise, and they have been developing the real, let's say, background, scientific background of this guideline, and that you will see later in this today. They will show you how to implement practically this test guideline. Next slide, please, Leslie. Well, this is the outline of the presentation of today. As I said, first we will I give you a little bit of background. We will continue explaining the principle of the method, describe how it is, how to do it in practice, and we also will refer a little bit to the interlaboratory calibration study that help us to validate the methods. A little bit regarding comparison of the proposed method of this method with other possible method for hydrophobicity and potential applications of this test guideline. And of course, you will have the opportunity, time allowing, to send us some questions, and we will try to answer them as well as we can. Please, Leslie, next slide. So, as you well know, the KOW, the octanol water partition coefficient, is a good indicator of the phase and transport of a chemical in the aquatic compartment, and is a parameter that is used, for example, in environmental exposure models, and as well a human risk assessment. So it is required in some legislative frameworks when registering or trying to put a new chemical substance in the market. However, we know is very well known, and there is a wide consensus that the KOW, the octanol water partitioning coefficient, is not applicable for the assessment of nanomaterials. So in the discussions in the OECD Working Party of Manufactured Nanomaterials, we conclude there was a need to develop some kind of method that could provide some information of the behavior of nanomaterials in fluids indeed, because as you know, octanol water partitioning is referring always to studies in a liquid, normally aqueous environment. This is what we have normally in human bodies or also in the environment. Please, next slide. So we knew that for chemicals in general, the hydrophobicity has a strong influence in cellular uptake, in the toxicity, immunity, immune response, interaction with immune cells and hemolysis, and absorption, for instance, of proteins. So hydrophobicity was identified as a relevant parameter by the OECD in the decision framework for manufacturing nanomaterials regarding physical chemical characterization. And it was considered that it could be a good tool to provide information on the interaction of nanomaterials with aquatic and terrestrial organisms, or as well with human cell surfaces. So that includes bioaccumulation, persistence, transport through skin and lungs, and then accumulated, let's say, toxicokinetics in a very wide sense. So, and we know as well that hydrophobicity is some relation, not directly, but it has some direction with the KOW. So there was some parallelism between the two parameters that could be useful to have. So next slide, please. Moreover, it is well known that, for instance, regarding biocompatibility of chemicals, the hydrophobicity together with size and surface charge are the main parameter influencing nanoparticle biocompatibility. So in 2019, in the OECD Test Guideline program, was include a project to develop a test guideline that should address the hydrophobicity of nanomaterials. And this was a proposal by the European Commission JRC to the OECD. And this was in 2019. And after some work, some years of works, commenting, discussion with experts, etc., as Mar has explained generally at the beginning of this webinar, the final new test guideline 126 determination of the hydrophobicity index of nanomaterials through an affinity measurement was approved in April 2023 by the OECD Test Guideline Program national coordinators, and indeed adopted later, I think it was in June 2023 by the Chemicals and Biotechnology Committee of the OECD, and published in June, July of 2023, or was it August? But it doesn't matter. So, as I said, this is the introduction, the background, general background for this test guideline. So now I think it's the turn for the next speaker that will explain you the principle of the method in general. So I think it's Chloe?
It's Andrea.
It's Andrea, sorry.
Thank you, Juan. So next slide, please. As Juan just highlighted, the measurement of the hydrophobicity of nanomaterials is really important. That's why we have been working a lot in the development of this test guideline. But I would like to start from the existing methods that were present even a few years ago when we started that were present on the market or in the scientific community to measure the hydrophobicity of nanomaterials. And I would like to show that all these methods had some limitations. The first method is the dye absorption method, in which you label the nanomaterials using an hydrophilic and an hydrophobic dye. The night blue is the hydrophilic, the rose bengal is the hydrophobic, and then by measuring the ratio of the number of molecules absorbed on the particles, you have a direct measurement of the hydrophobicity. So if the particle absorb more rose bengal than the night blue, they are tendentially hydrophobic. This method is relatively simple, but as we will also show at the end of the presentation, I think Chloe will show it, it is not really specific because these chemicals are binding in a very non-specific way to all the particles. So they cannot distinguish really between different degrees of hydrophilicity, hydrophobicity. The second method is based on column chromatography. So basically you have three different materials in the column, which increase in degree of hydrophobicity. Then you pass through the column your nanomaterial using an elution agent, and you measure the affinity of the nanomaterial to the column. Actually, this method is relatively similar to what we are doing in our method. So it is really accurate because it measures the affinity of the material, of the nanomaterial to the hydrophobic column. But it has the big disadvantage that is really expensive because you need to use a column that costs quite a few hundreds of euros for the three different chemicals. And then you also need the large volume of your nanomaterials. And this is not always the case. For example, if you want to measure the hydrophobicity of nanomedicine or a nanomaterial which is present at very, very small concentration. The third method is the contact angle, which is, let's say, the golden standard for measuring the hydrophobicity of flat surfaces. So basically, you leave a droplet of water on a surface, and with a goniometer, you measure the contact angle, which is formed between the droplet of water and the surface. This is a very simple method, and which is largely used to measure the hydrophobicity of flat surfaces. If you want to use it for nanomaterials, you can do that. The problem is that you need to create an homogeneous film of your nanomaterial in dry conditions. So you need a large volume of nanomaterials again, and it is not really accurate because the measurement of the hydrophobicity comes from a mathematical modeling, which requires that your material is flat. And when you use a film made by nanoparticles, this is not flat by definition. So this method is not really accurate. So this next slide, please. This was the, let's say, one of the reasons why we decided to start this project. So to develop a method which is based to the affinity of the nanomaterial to collectors, to surfaces. Actually, we have a surface which is hydrophobic, which is our hydrophobic collector. And then we have two surfaces which are hydrophilic. One is negatively charged and one is positively charged. And then by means of dark field microscopy, we are able to count in time the number of particles which are binding in real time to the different collector surfaces. So what is the advantage? So it's very similar to an affinity column because we measure the affinity, but we are doing the same in a microfluidic channel that requires only very few microliters of your sample and a very low concentration of your sample. So if you can play the two videos, I can show that, for example, an hydrophobic particle, which is binding to the hydrophobic collector, is the binding rate is very high. So you see now displaying, you see that a lot of particles in time are binding with a high rate, while the same particle on the negatively charged hydrophobic, the T4, the negatively charged hydrophilic collector, they are not binding at all. So this is showing that the particles have different affinities for the different collectors. So this is the principle that we are using for measuring the hydrophobicity of the particles. Next slide. So the method principle is that we are measuring the affinity to engineered surfaces, and by using the ratio between the three different affinities on the three different collectors that I showed in the previous slide, we are able to measure a value, a number, which is the hydrophobicity index. And this enables us to characterize and quantify the hydrophobicity of the nanomaterials. Next slide. There is a theory behind this method. So if you look at the left-hand side of the slide, when a nanomaterial, a nanoparticle in dispersion is in contact or is very close to the hydrophobic collector, the extended LBO theory, which is the theory which regulates the interaction between the particle and the surface, tells us that there is a very low energy barrier that the particle has to overcome before getting in close contact with the surface and being immobilized by the surface. So this energy barrier that can be calculated from the extended LBO theory is of the order of magnitude of 0.1, 0.2 kT. So this means that the thermal energy is able to make the particle to diffuse and get in contact with the surface and get immobilized by the hydrophobic surface. So in this case, we have an high rate of binding of the particles on the surface, which is translated in the curve that it is just below. As a function of the time, we have a certain rate of absorption of the nanomaterials. What happens if I have an hydrophilic nanomaterial? In this case, the extended LBO theory tells us that there is a relatively high energy barrier for the particle to get in contact with the surface, which is around a few kT values. This means that the thermal energy is not enough to make the particle to overcome the energy barriers. The particle prefers to stay in the water dispersion, and the relative binding rate of the particles on the collector is really low. And this is translated in a very, very low binding rate, almost zero binding rate of the particles to the collector. What happens also if we don't have any energy barrier? So this happens, for example, when I have a collector characterized by an opposite charge than the one present on the particle. So if I have an opposite charge, there is no energy barrier, so the particles are free to bind on the collector. And this is how we measure the maximum velocity, the maximum binding rate of the particles on the collector. So this is our normalization factor, let's say. So how we defined the hydrophobicity index. The hydrophobicity index is the log of the velocity of binding of the particles on the hydrophobic collector, normalized to the maximum velocity of the particles on the collector without energy barrier. So this means that we are measuring a ratio of particles that prefer to stay on the hydrophobic collector instead of staying in the water dispersion. And I think you can go to the next slide, please. So what is the output of our measurement? The output of our measurement is the hydrophobicity index, which is a number. It is a value. The maximum value that this number can have is 0. So if the velocity of the binding to the hydrophobic collector is very close to the one of the maximum velocity. So we defined, just to give an idea, that a material is hydrophobic when the H index is close to 0. And then if we think that only, for example, only 10% of particles are binding on T0 on the hydrophobic collector compared to the maximum velocity, the hydrophobicity index would be -1. So we can define that a material which has an hydrophobicity index lower than -1 is an hydrophilic material. So we also have a scale, a degree that that can define the degree of hydrophobicity of the nanomaterials that we are characterizing. Next slide. So the method returns to you an hydrophobicity index. Of course, the measurement of the hydrophobicity index is done in specific experimental conditions, and also the validity of the method is limited to these conditions. Of course, it depends on the pH of the suspension, the salt concentration, the presence of surfactants. What we did during the development of the test guideline, and in particular in the instructions, we standardized, let's say, during the development and in the interlaboratory study, we defined those conditions at which the best conditions at which this measurement has to be done. The second very important thing is that this method works also for poorly dispersible hydrophobic nanomaterials, which means that they are really hydrophobic. And then my colleague Chloé a bit later on will show that we can, for example, disperse this material using a surfactant and different concentration, and we can extrapolate the value of the hydrophobicity index when the concentration of the surfactant is 0. So this also enables us to measure the hydrophobicity index for really hydrophobic nanomaterials. And then during our work during this year, within the development of the test guideline, but also with other many different projects we have in this framework, we demonstrated that the technique has a broad applicability to different materials. So we measured gold, silver nanoparticles, titania, silica, zinc oxide, gallium nitride, ceria, but also we measured the hydrophobicity of novel pollutants like the nanoplastics or nanomedicines like liposomes or other liposome-based nanomaterials. So we measured really many different materials, and most of the cases we published the result in scientific papers. So in terms of applicability, in terms of number of materials, we were basing our study on the list of the representative nanomaterials we have in our nanomaterials repository we have here at the JRC. And as you can see from the table, we could measure the hydrophobicity index of most of the materials we had. What we couldn't measure is the hydrophobicity index of very small nanomaterials. This is basically due to the limitation of the dark field microscopy detection. So we are not able to detect, for example, carbon nanotubes or fullerenes or graphene. But there are alternatives to measure the affinity of these materials to our collectors. There are alternative techniques, and if you are interested, at the end of the presentation, I can show, I can explain what are the alternatives to the dark field detection. And I think this was my last slide. So now I will pass the word to Francesco, who will show the description of the method.
Thank you, Andrea, for giving me the floor. Next slide, please. Today, I'm gonna describe you step by step the method for the determination of the hydrophobicity index. So in the first step is related to the nanomaterial sample preparation, which has to be in a stable dispersion. The second step is the measurement of the affinity of this material to engineered collectors through dark field microscopy. And the third and last step is the calculation of the absorption rate in terms of affinity of these materials on three collectors and the determination of the hydrophobicity index of the nanomaterials. Next slide, please. To perform in your own laboratory the experiment, what do you need? You need for sure your test nanomaterials together with the measurement buffer. You need 3 different collectors with different surface properties, 1 micropipette, a dark field microscope equipped with a camera, a computer, and the test guideline standard operating procedure that we wrote before the interlaboratory comparison study. And then you need for the calculation of the affinity of these materials for the collectors, the software ImageJ plus its plugin TrackMate that are freely downloadable, a spreadsheet program like an Excel file, for example, and again the test guideline standard operating procedure. Next slide, please. The nanomaterial sample can be in 2 different forms, powder or dispersion. What is really important is that to disperse the nanomaterial, you use a protocol very mild to avoid the disruption of potential coating. And it's important also to use a buffer to disperse the sample, so salt with a no concentration and a known pH value. As optional, you can also perform a little bit physicochemical characterization of your materials in terms of size and zeta potential through dynamic light scattering. Next, please. To develop our method, we prepare 3 different collectors, starting from a classical glass slide. We produce 3 different collectors, 1 hydrophobic coated with a Teflon-like polymer, 1 hydrophilic positively charged and 1 hydrophilic negatively charged, in order to test different material with different surface charge, both positive and negative. All these collectors are mounted with a 16-channel monofluidic cell to allow us the injection of the sample in the channel. Next, please. The measurement, as explained before by Andrea, is based on the injection of your tested material inside the channel of the microfluidic cell mounted on the collector. Then you put your collector under the microscope and you make the focus, and you are able to measure in real time the affinity of your particles for the collector with a sensitivity of 1 particle thanks to the dark-field microscopy technique. The output of your measure is an image sequence of 25 frames that you can see on the right of the screen. Next, please. So once you have the image sequence of 25 frames recorded in 12 minutes, you can perform the analysis with an automatized software installed inside ImageA that allow you to detect and track all the particles on the surface. Once you have this data, you are able to calculate the banding curves of the material on the 3 different collectors, and then to determine the hydrophobicity index that is defined as the logarithm of the ratio between the adsorption rate, the binding rate of our nanomaterial on the hydrophobic collector and the binding rate of our nanomaterial on the collector with the minimum with the maximum attachment. And after this, the output is that a nanomaterial is considered hydrophobic if the value of the hydrophobicity index is between 0 and -1, while is hydrophilic is if the value of the hydrophobicity index is below -1. So we can say that -1 is the cutoff value to distinguish between hydrophobic and hydrophilic nanomaterial. Next, please. Next, thanks. Now I will show you a short video of the test in practice, in particular the part related to the detection of the materials under the microscope. So you have to prepare the sample according to the standard operating procedure. When the sample is ready, you will fill one of the channel of the microfluidic chamber on the top of the collectors with a micropipette. You can see the dispersion flowing inside the channel. And then you place the collector under your microscope. You adjust the focus. You put the image in a clean view area, and then you set up all the parameters and you start the recording of the images. You repeat this operation for all the 3 collectors for each samples, and then you proceed with the data analysis. Next, please. Now I will talk a little bit how to deal with the poorly dispersible nanomaterials. When we started drafting the test guideline, we consider only that our method was applicable to nanomaterials in stable dispersion in aqueous medium. But during different comments round together with different experts, we were able to introduce also the characterization of the hydrophobicity index of very hydrophobic nanomaterial that are per definition, poorly dispersible in water. Here, I will present you the example of the titanium dioxide with a dimeticone coated, which is really hydrophobic. Next, please. To disperse these hydrophobic nanomaterials, we used a surfactant. And here you can see a graph which is a direct relation between the hydrophobicity index and the ratio of surfactant to nanoparticles. We use 4 different ratios, and we were enabled to extrapolate the value of the hydrophobicity index that the material would have for the material without coating would have. This is really important because without this extrapolation method, you cannot have an hydrophobicity index for hydrophobic material that are not dispersible in aqueous medium. On the right, you can see also a scale of the different value of the hydrophobicity index for different tested materials. Next, please. Our characterization method was firstly applied to gold nanoparticles coated with the polyethylene oxide, and all the results were published in a paper of 2018. As you can see at the top of the slides, the water-ethanol partition coefficient doesn't work for hydrophobic nanomaterials because they tend to aggregate at the interface. But thanks to our method based on dark field microscopy, which allow to measure the binding affinity of our material on 3 different collectors, we were able to determine the value of the hydrophobicity index of gold nanoparticles without the PO coating, which are very hydrophobic, as you can see from the graph. And then by adding different percentage of PO nanoparticles coverage, you can see that the hydrophobicity index decreases by adding a different amount of PO and becomes for sure more hydrophilic. And you can see also that we reach the maximum of the hydrophilicity of our material for coverage of the particle around 50%. I think that this is my last slide, and I will give the floor to my colleague Chloé Desmet that explain a little bit on the ELC validation. Thank you.
Thanks, Francesco. So next slide, please. So in the context of the development of the test guideline, we organized an interlaboratory comparison exercise together with the help of the expert group. This interlaboratory comparison is divided in 3 main steps. The first one consists in detecting one control sample in order to verify that each of the participants can detect effectively this sample with their own microscope and camera setup. The second step is the measurement of the affinity of different materials for the 3 collectors. And the last one is the determination of the hydrophobicity index. So the comparison of the result obtained by each laboratory after each of the steps permit to assess the transferability, the reproducibility, and the robustness of the standard operating procedure that was developed with the test guideline. And this is done independently from the dark field microscopy setup, the camera, the software, and everything. Next slide, please. So for the interlaboratory comparison, we had 9 participants, and there were entities from US, France, Greece, Italy, Germany, Portugal, UK, and we did the test ourselves. We distributed 3 different materials for each laboratory. One was given to all of the laboratory as the control material. And each of the sample was tested at least by 5 laboratories. Next, please. So the 5 materials that were tested were provided by GRC or as a powder or as a dispersion. So for the powder, we also provided the SOP to obtain the same dispersion for all the laboratories. The samples tested were commercial polystyrene that was hydrophobic, gold nanoparticles stabilized in citrate, carboxylate polystyrene that is more hydrophilic, titanium dioxide from the GRC Nanomaterials repository, and the commercial food additive, which is also titanium dioxide. Next, please. We distributed to each laboratory a test kit containing the 3 collectors, so our 3 surfaces with 16 fluidic channels that can be directly used for testing the nanomaterial, the 3 material samples, and a calibration chip for the microscope. We also provided the SOP and some tools to ease data treatment. Next, please. So I will not spend too much time on the evaluation of the result. You can find all the details in the GRC technical report that was published about it. You can see here the cover. But in brief, all steps were evaluated using ISO standard statistical analysis. And the final result of the test, which is the determination of the hydrophobicity index of the different materials, you can see it as the main graph on the slide. So for the evaluation of this main result as our hydrophobicity index, all results were considered satisfactory, with all the data scores being below 2. So this result permitted to validate the use of the SOP to measure the hydrophobicity index of the tested material through the affinity measurement. Next slide, please. So now that you are familiar with the method and how to do it in practice and how it has been validated, I will now tell you a bit more about a study that we recently performed in order to compare this method with another one available, presented at the beginning of the webinar, which is the dye adsorption method. Next, please. So as my colleague presented earlier, the dye adsorption method is simple since it's based on the interaction of chemical dyes with the nanomaterials. But this method has important drawbacks. Both methods, dye adsorption and hydrophobicity index, are based on affinity of the nanomaterials. In one case with chemicals, and in the other one, the affinity for stationary surfaces. In the case of chemicals, there is a very high influence of the surface topography, while the hydrophobicity index is much less sensitive to that, simply due to the size difference as represented on the figure, with small chemicals binding on bigger particles in one case versus the small particle binding on large surface in the other one. The applicability of the 2 methods is different. One could be more appropriated, for instance, for the transport of toxicant, while the hydrophobicity index is maybe more applicable to biodistribution, for instance. Next, please. So here is the visual representation of the fact that sometimes dye adsorption is not really well suited for hydrophobicity assessment. I don't ask you to read the number in the table, but just to look at the color. So on the left hand, the result of the dye adsorption method for the same material as in the left side on the hydrophobicity index. And you can compare the color with the reference scale for both methods. So as you can see, the dye adsorption method for these different nanomaterials, which were silver nanoparticles with different surface coverage, was not well suited because it gave the same result of hydrophobicity for all of the particles. While on the hydrophobicity index, on the right-hand side, we have the materials that are more distributed on the scale. So as I said before, both methods could be valid, but they would be applicable for different uses. Next, please. So now we know how to measure the hydrophobicity index, but what could be the use of such a parameter? And that's what I will try to answer now. Next, please. The method was applied for the characterization of nanoplastics thanks to a collaboration with a French university. And we try to correlate the nanoplastics properties to their fate in the environment. Here we tested particles based on carboxylated polystyrene with different molar concentration of carboxylic monomer. Two types of monomer were used for the synthesis, and we wanted to assess the effect of the type of monomer as well as the molar content used in the synthesis. We also tested primary nanoplastics obtained from grinded polystyrene. Next slide, please. Okay. So here we quantify the hydrophobicity of the different nanoplastics. So in the bar chart, the closer the bar is to the reference with water, the higher is the hydrophilicity. So the smaller the bar is, the more hydrophobic is the material. So we can note that the two different moieties give different hydrophobicity character to the nanomaterial, and the hydrophobicity degree of the particle increase with the carboxyl content. So these results were presented in the two studies that are cited on the bottom of the slide. And the properties of the particles were assessed together with the environmental fate in sand, for example. Next slide, please. We also started to study the potential effect of hydrophobicity on bioaccumulation by performing contact tests with the nanomaterial on two different species of freshwater microalgae. So here we measure the average number of particles that were binding to the algae, and to assess a possible correlation between the hydrophobicity index and the attachment on the algae surface. So you can see here on the graph the hydrophobicity index that is presented as a function of the number of particles per algae that was measured. So those first results look promising, with clear differences between hydrophobic and hydrophilic material. And there is a trend between the two parameters, but this study is ongoing and we have to evaluate more material. Also, we want to evaluate the impact of the hydrophobicity of nanomaterial on cell uptake, on cell viability, and physiological parameters such as oxidative stress. Next, please. Finally, maybe the hydrophobicity index could be used as a predictor of the attachment efficiency. Heteroaggregation is the aggregation process between particles of different types. For instance, if nanomaterials are in contact with sand or an environmental matrix. And so the attachment efficiency is the probability of forming heteroaggregate. And it's one very important fate descriptor. However, there is currently no standard method to assess this attachment efficiency parameter. And one of the proposed methods coming from the European project Nanophase is the batch test, but it's a long experimental procedure. So next slide, please. We then wanted to study the attachment efficiency of some of the nanomaterials from the ILC using EU reference soil. So we adapted the batch test method described in the paper cited here. And we filtrated the samples to remove aggregates at different time points. And we measured the concentration of the single particles that remains in the sample, following a method that was developed in our lab by my colleague Andrea. So the first results here are promising, as you can see from the curve on the bottom of the slide, with there seems to be a trend between the hydrophobicity index and the attachment efficiency. But again, this study should go much further with a large batch of nanomaterial tested. And we are planning a collaboration on this topic to really study the potential correlation. Next, please. So I presented the different studies that we started ourselves to evaluate the potential uses and correlation of the parameter that we proposed in the TG. But most importantly, we hope that the TG will be used to generate data. To determine the hydrophobicity index of many nanomaterial and be able to investigate then the relationship with fate and environmental behavior, for instance, or relate with toxicity or transport together with the other properties that a nanomaterial can have. Next, please. So if you want to know more, of course, there is the test guideline. There is also the GRC technical report that was published and the 2 papers that we published during the development of the method and the different papers on the application of the method for different types of nanoparticles. We are still working, as I said before, on the correlations with bioaccumulation and heteroaggregation. Next, please. We would like to thank, of course, all the participants of the interlaboratory comparison, as well as the expert group that was started in 2019. All collaboration, the OECD national experts and coordinators that evaluated the test guideline, and the OECD Secretariat. Next, please. Okay, that was my last slide, so we will be happy to answer the questions.
Thank you so much to the 4 of you for this very thorough explanation. I think we have a number of questions, so perhaps I can invite you to turn your cameras on. I'm checking on my other screen that what is the type of view that we have. And you should have received in the Q&A all the questions. So I would appreciate, I mean, perhaps some of them were already answered during the presentations, but if you can go through them and select the one that you wish to answer yourself, and please take the floor.
Yeah, maybe can I start to answer to a few of them?
Sure. Hold on just a little bit. Kimika, perhaps you can just stop sharing so we have all the speakers on the screen. Voila. Thank you.
Shall I start from the first one because there are quite a few?
Yes, but our audience cannot see the questions. So when you answer, just please select the options so they are we can see that they have been answered.
Okay, so the first question is background of the TG 126 was KOW, but the method doesn't allow to refer to the KOW. Can you clarify? Actually, yeah, there is a relation, let's say, with the KOW. In our case, we are measuring if the nanomaterial prefers to stay in the water dispersion or on the hydrophobic collector. So that's the, let's say, relationship with the KOW, where the chemical prefers to stay in the water or in the octanol phase. So this is the only thing that we can say about the relationship with the KOW. So there is this kind of similar principle, let's say, of the measurement. Okay. Then should I go question by question?
Yes, answer the questions that you wish, and I will just make them live.
Okay, so the second question is, how was hydrophobicity defined for particles? That's a good question. Actually, hydrophobicity, there is not a definition of hydrophobicity. There is a description of hydrophobicity, which is the tendency of a material or a chemical or a substance to repel the water. There are different ways of measuring the hydrophobicity, as you could see, for flat surfaces and in a more difficult way for nanomaterials. So we haven't made any new definition of hydrophobicity. We just made a new method for measuring or scaling the hydrophobicity of nanomaterials. Then I'm wondering if methods for determining water sorption isotherms, sorption balance, for example, have been considered as relevant methods. Yes, of course, my slide with the previous method was not containing all the methods for measuring the hydrophobicity. We know that there are many more. So we know that there is this method. We considered it. I think in the test guideline, if I don't remember wrongly, or maybe we did it for the SPSF, Juan help me, we did
I don't remember.
a comparison with of the methods in terms of pros and cons and how our method was positioned compared to the others.
In the SPSF.
Yeah. In the SPSF. But
just to clarify, the SPSF, for those that are not aware, is like the standard project submission form, which is like the project proposal that goes to the OECD, justifying the rational regulatory relevance, etc., for the national coordinators to agree to proceed with the proposal. Sorry. Yeah.
Then, shall I go on? The definition. Tell me for the other speakers if you want to answer the questions. I don't want to monopolize the floor. Huh? I just if I'm able to reply.
Maybe I can give a general answer to answer to a few questions, because actually there are many questions about the stable dispersion. Someone asked how stable dispersion is defined. A hydrophobic material may not even be wetted. Or what about not stable dispersion? Is it possible to determine the hydrophobicity index? And when you have coatings and surfactants in place, technically the index corresponds to a modified material, not the original one. So you probably want to characterize and one you actually observe in the product. Is that correct? So all of those questions are related to the dispersion, and I think we try to answer this issue in the part of extrapolation. So indeed, what we measure with the hydrophobicity index is the hydrophobicity of the material as it is in the dispersion. So yes, you measure the hydrophobicity also with the coating. For instance, if you measure two different titanium dioxide nanoparticles, if they have two different coatings, they won't have the same hydrophobicity index. If you want to stabilize the material, you use a surfactant. It can be, it's another question, it can be any type of surfactant you can use, for instance, as we did, natural organic matter, such as humic acid. And here you will modify the hydrophobicity index of the bare particle to make it stable. So when you measure the hydrophobicity index in this context, it won't be the hydrophobicity index of the bare material, but the one modified. So using the extrapolation, so using different concentration of the surfactant, then you can extrapolate to the hydrophobicity index of the material without any surfactant. But yes, it's not the hydrophobicity of the pure material, let's say.
Thank you, Chloe. If you can just click on the answers that you have already responded, so we can make sure that everybody can see them, and they are being recorded, so you will be able to go back to them.
I can answer to the question, is it possible to apply the method for carbon nanotubes? Because it's something that I mentioned during my presentation. Yes, it is. I mean, the method in principle, so how the hydrophobicity index is measured is the ratio between the binding rate on the hydrophobic collector with the binding rate on the opposite charge collector. So that's the principle and how mathematically the H index is measured. So as long as you have a method for measuring a binding rate of a material towards a collector, you can measure the H index. So for carbon nanotubes, if you have a method like I don't know, a real-time biosensing system like SPR or QCM, and you're able to discriminate between the binding curve of the carbon nanotubes and, for example, the dispersant that you have inside, then you can use this method. Or you can use also electron microscopy, for example, but you need to make time points in order to measure the binding rate. So there are alternatives to the dark field. Why we focused on the dark field? Because it is very convenient as a technique, is a let's say a standard microscopy technique, and as we showed, it can be applied to most of the nanomaterials we had in our repository, and we could apply it to many nanomaterials. But any technique that measures binding rates can be used to calculate the H index. So we also invite, if you are expert in one of those techniques, to use the same principle to measure this parameter.
Maybe I can answer about the two questions on how to get the collectors for the method. So at the moment, we can give to the interested laboratory the protocol to fabricate by themselves the collector in a quite easy way. But we are currently working in collaboration with a company expert in surfaces modification to try to standardize the production of the 3 collectors in order that we hope in a near future we can also give you a link to the shop of this company to buy the whole set of the collector.
So we keep receiving some questions. So if my speakers can just make sure to let me know if there are other questions that they are able to answer.
Yeah, for example, does this hydrophobicity index has been compared with the data produced with the available methods? Yes, we did it as Chloe showed with the dye absorption, and we got, I don't want to say we got different results. We proved that the two methods that are supposed to measure the same thing are actually measuring 2 different things. So this is a difficult answer that has to be considered case by case. For example, we compared most of the materials with a contact angle. And if you start with an hydrophobic material that you have available in your lab, and you can make a nice surface with your material pelleted on the surface and measure the contact angle, you measure something which is hydrophobic, then material will result hydrophobic also from our measurement. So actually there is a good correlation in this case. But this has to be done case by case, technique by technique, because the techniques are measuring different things because they are based on different measuring principles. Then there are many, or at least a few questions about the influence of the presence of surfactant or the zeta potential. And I think to all these questions, I think we already presented the results during the webinar. Actually, in the test guideline, we standardized the conditions to measure the hydrophobicity, which depends on the pH and the soil concentration, the surfactant, the presence of the surfactants, for example. And this influences also the zeta potential of the particles. So it is important to compare the results in a standard way. And we showed how to extrapolate, for example, the value of the hydrophobicity index in the presence of the surfactant. So the answer is yes, the presence of a surfactant is influencing, but you can extrapolate the value without the surfactant using the method that Chloe showed.
Thank you. And I think you have also merged some of the questions that we have received that were quite similar. Just perhaps just asking and making sure, Juan, Francesco, Chloe, if there's anything that you see there that you think has not been answered from your presentations.
Maybe I can answer to a question on how positive and negatively charged surface were realized. So starting from the hydrophobic collector, which is Teflon-like coated with simple self-assembly of different polyelectrolytes by simply dipping the hydrophobic glass slide into different solution of polyelectrolytes. We perform a layer by layer deposition for one collector with final polyelectrolytes, a final layer of polyelectrolytes with a positive charge, and for the other one with a polyelectrolyte, final polyelectrolytes with a negative charge.
There is a question which is quite interesting about how do you avoid sedimentation on the collector, which can influence number of particles on the collector, and how do you address different refractive indices, and therefore different light scattering intensity, so as the intensity refracted light dependent on the particle size. Yeah, sedimentation, we can't avoid the sedimentation. Actually, we measure the binding rate of the particles on the bottom side. So it means that the gravity has an influence. Simply by the measurement is relatively fast. So we measure the binding rate of about 12 minutes, if I'm not remembering wrongly. So during this time, for most of the particles, the sedimentation can be neglected. So only diffusion is participating to the binding rate of the particles. So the answer is yes, it has an influence, but we know it and we try to neglect it by measuring quickly the binding rate of the particles. And the light scattering, yes, if there are aggregates or larger particles in the dispersion, they scatter more light. But what we do, we simply count the particles. So we are not looking at the light intensity. When we calculate the binding rate, we treat one single like hotspot as a single particle. So we don't care if it scatters more or less light. We consider it as a single particle that binds to the surface.
One other question is about the E171, that is an untreated anatase. Why would it be hydrophobic? So here maybe we should clarify that the method is not only for hydrophobic material. The hydrophobicity index is defined as a scale of hydrophobicity. So you can measure hydrophilic and hydrophobic material in different ranges of hydrophobicity. So no, we don't expect this material to be especially hydrophobic. Another question is the hydrophobicity index influenced by the agglomeration and aggregation state of the particles? Andrea partly answered to that. I wanted also to give the example of the titanium dioxide that has a hydrophobic coating that we have in the GRC nanomaterial repository, where the primary size of the particle is 21 nanometer. But practically, this material doesn't exist at this size if you want to have it in a liquid medium, because it is too hydrophobic. So when you measure it, you measure the hydrophobicity of the aggregate of the nanomaterial in this case. So for material that are not stable, you would measure the average hydrophobicity index of the aggregates, and it would be, of course, influenced by the aggregation state.
Then we have a question about the minimum requirements on the dark field microscope. Actually, any let's say basic dark field microscope can be used. Maybe you need to be a bit careful on the camera that you have, but for example, what we did in the IELC, we compared. You can read it in the report, in the JRC report. We compared. I mean, in the different laboratories, they had different microscopes with different cameras, and all of them they were able to detect the materials we sent. So I would say that a standard dark field microscope works for the materials that we showed. There are some, let's say, special dark field microscopes with special. I don't want to make advertisements, but for example, the Cytoviva microscope. which is basically an enhanced dark field microscope. In this case, you can lower the sensitivity of your microscope and detect particles which are smaller than the particles that we showed. So you can detect, for example, gold, silver nanoparticles as small as 10, 15 nanometers in size. So these also enlarge the applicability of the method, even using a dark field microscope.
There is a question about a test that we could recommend to predict potential dispersibility issues. I don't want to sound too simplistic, but I think if you put the powder in water, you will quickly see if you will have dispersibility issues, because something that is hydrophilic or something that is really hydrophobic, you cannot even wet the particles. Then about the concentration of particles that is used for our test to have enough particles to have good statistical analysis, we tend to use 10 to the 5 particle per ml. The measurement principle as quotient of velocities is not clear to me. Could you please explain? So what we measure is the number of particles binding by unit of time. So you inject your nanoparticle sample and you count the number of particles at 30 seconds, 1 minute, 1 minute and 30 seconds, etc. So that you can define the binding rates and the binding velocities. Then you compare the velocity on due to the hydrophobic forces, so on the hydrophobic collector, compared to the maximum velocity that you obtain with maximizing the electrostatic forces. And here you have the influence of the hydrophobicity. And that's why we use this quotient of velocities to define the hydrophobicity index. The positive and negative surfaces, how they were realized, we use the self-assembled monolayer method. So we simply dip a very hydrophobic microscope slide in 2 different chemicals, one that is negatively charged and one that is positively charged. And we obtain a positive or negative layer on top of the slide.
Okay, I can see that you're still reading. I mean, we have tons of questions, so it's difficult to identify which one. But perhaps I can just give you one before we close. If you can just look, if you want to make any final statement. I think what we're going to be doing is to also to keep the questions and share them with you, because I think this can help you as we move forward, and for the audience also to know that if there are any pending questions, you can always contact the Secretariat so we can redirect you to the appropriate person. But is there anything else that you wish to share with us today, to our experts? I mean, it has been quite detailed, but I just think that I want to give you the floor before we close this adventure, at least on this occasion.
Well, if I can speak, I think we are very happy of presenting our method, and we really hope that we can discuss more with the experts and that we can have collaborations and have this method applied to more nanomaterials so that we can gather more data and learn more about the usefulness of the method. Yeah. Thanks to all.
No, thank you, and thank you to the four of you for all your intensive work during these years. Just for our participants, I mean, there are some links that have been shared during the chat where you can just sign up if you want to receive some news. There are some past webinars on other test guidelines that have been shared. Webinars that relate to the OECD Test Guidelines program, validation, etc. How does it work? How can you be involved? But do not worry if you miss any of these chats, these chat messages. You will be receiving as a participant for this call the link to this webinar and to the other material that can be made available to you. So Kimiko, if you can just add the last slide so we can just bring this workshop to a conclusion. So you have some links there. We invite you to join and to sign up. And with this, I just want to thank our four panelists, our four experts for all the intensive exchanges over the past years, and we wish you a very successful continuation. And for those of you on the audience, please use the test guidelines, give us feedback. The idea is to make all of your life easier, and if there's something that needs to be clarified, it should be clarified, and we look forward to have you with us at the next webinar. So thank you so much to everyone, and see you soon.